Today we'll talk about the joint work with Massimo Giulietti and Arianna Sabatini on the construction of linear codes for private information retrieval. So first of all, let me recall a few basic facts on linear codes. A linear code C is a linear subspace of Ft to the n, then n is the length of the code, while the dimension k of the code is the dimension of C as a linear space over Fq. For a code C with these parameters, I'll write nkq code. Also, for an nkq code C, a generator matrix is a k by n matrix whose rows are a basis of C. And in this case, we can write C as the set of vectors x times g, where g is a generator matrix and x runs over Fq to the k. Before introducing the class of linear codes that we have studied, I would like to show which is the context in which these codes find an application. And so consider the following situation in which we have a database, which for us is a binary string, x1, x2, xm, and there is a user who wants to retrieve an item from the database, but without disclosing any information on the item being retrieved. So for instance, the user wants to retrieve xi, but without giving information on the index I. This problem is called private information retrieval. One possible trivial solution to this problem could be for the user to download the entire database, because in this case, clearly the user can retrieve xi, and also clearly is not giving any information on I. The problem of this solution, this trivial solution, is its communication cost, which is defined as the number of bits exchanged between the database and the user, and which for this trivial solution is linear in the length of the database. So one may ask if it is possible to do better in terms of communication cost, and well, Chor, Kushilevich, Goldreich, and Sudan proved that actually the trivial solution is the best possible if we assume that the database is stored on a single server. So if we want to achieve private information retrieval with a sublinear communication cost, we must look at a different context. And so Chor and the others in their paper consider the following situation in which the database is replicated among several servers, and they also assume that these servers do not communicate with each other. Under these assumptions, they can prove that it is possible to reduce the communication cost. And in particular, they prove that this cost is for two non-communicating servers, something which is roughly m to 1 over 3. And for k non-communicating servers, it is roughly m to 1 over k. To achieve this result, they use so-called PIR protocols, protocols for private information retrieval, which are based on the idea that if the servers do not communicate, then it is possible to send a set of queries to the different servers in such a way that the answers to these queries allow the user to retrieve the item, but no information is given to any single server. Since this seminal paper in 1998, much more has been done in terms of reducing the communication cost of PIR protocols, but one common problem that these protocols share is that they do not consider another cost parameter which is involved, that is the so-called storage overhead. The storage overhead is defined as the ratio between the total number of bits that are stored on all the servers and the number of bits stored in the database. So in the protocols that we have seen before, where the database was simply replicated, the storage overhead was exactly the number of servers used, and so this number was at least 2. However, if the database is very large, this approach could be unfeasible for certain applications. So the question is, if we can construct, if we can obtain private information retrieval with a low communication cost, but also with a lower storage overhead, so without doubling or worse the number of bits that we need to store. And Faselli, Vardi, and Jacobi proved that this is actually possible if we assume that the database is first encoded in a particular way, and then this encoded version of the database is divided among several servers. In order to apply the approach of Faselli, Vardi, and Jacobi, two main ingredients are needed. First of all, we need a particular type of linear code and these are the so-called PIR codes, codes for private information retrieval. And then we need a PIR protocol that must be applied on the encoded version of the database. From now on, I will only consider the first of these two ingredients, so I will focus on this class of linear codes. And here you can see the definition. So a K-server PIR code is a binary code, let's say of length m and dimension s, that admits a generator matrix with the following property, that for every integer I between 1 and the dimension of the code, we can find k disjoint subsets of columns of this generator matrix that add up to the vector ei, where ei is the vector with all zeros and 1 in position I. If we apply the approach of Faselli, Vardi, and Jacobi with a K-server PIR code with these parameters, then m, the length of the code, is the total number of bits that are stored in all the servers. The dimension of the code is the number of bits in the database, and so the storage overhead of this protocol is m over s. Since we want to minimize the storage overhead of the protocol, for given k and s, we want to minimize m. So basically, if we fix the number of servers and the dimension of the code, we want to find the shortest possible PIR code. Here you can see an example. Consider the code associated with this generator matrix G. It is possible to see that this is a 3-server PIR code. What we need to prove is that for each of these vectors from E1 to E5, we can find k disjoint choices of columns of G whose sum is ei. So for instance, let's start with E1. Clearly, E1 is the first column of G, but E1 is also the sum of these 4 columns of G. And we also have another choice, because E1 is the sum of the second, the fourth, and the 6th column of G. So we found 3 disjoint choices of columns of G that add up to E1. And the same can be done with the other vectors, showing that C is actually a 3-server PIR code. Okay, so one of the starting points of our paper was a result by Faselli, Vardi, and Jacobi that now I'm going to show. First of all, I need a quick observation that if we take a set S of subsets S1, SR of the set of numbers from 1 to S, then it is possible to associate to this set a linear code that I will denote by C of S. That is the linear code that encodes the vector x1, xs into the vector x1, xs, p1, pr, where these R redundancy bits are defined by this rule. So you can see that pi depends on the subset Si. Faselli, Vardi, and Jacobi provided a set of sufficient conditions on S so that this code, C of S, is a PIR code. So these are the conditions. First of all, we need that all these sets have size at least 2. Then we need that for every number from 1 to S, this number appears at least in k-1 of these subsets for some k. And finally, we need that 2 distinct subsets intersect, meet at most in 1 element. If these properties are true, then C of S is a K-server, where this K depends on property 2, PIR code of length S plus R and dimension S. Clearly, this lemma has a combinatorial flavor and shows that tools from finite geometry and design theory could be useful to construct PIR codes. So motivated by this result, we gave the following definition. Take a finite set X of size S. Then we say that the K partial packing of X is a set of k-1 partitions of X with the following 2 properties, that each subset in any partition has size at least 2, and then 2 subsets from 2 distinct partitions meet at most in 1 element. We also say that the order of a K partial packing is the total number of subsets that belong to these k-1 partitions that we chose. What is the connection of this definition with the previous slide? Well, it is easy to see that if we take S1 SR as the set of subsets of X that belong to these k-1 partitions, then it is possible to apply the previous lemma to this choice. Indeed, what we need to prove is that these sets have size at least 2, and this is guaranteed by property A. Then we need that two distinct subsets meet at most in one element, and this is guaranteed by property B. And finally, we need to check that for every element of X, this element belongs to at least k-1 of these subsets. And this is also true because we are taking these subsets from k-1 partitions of X. So at this point, we can apply the lemma of the previous slide, and we can see that from a k-partial packing of order R of a set of size S, we obtain a k-server PIR code with this length, R plus S, and this dimension S. So at this point, we wanted to look for examples of k-partial packings of certain sets X. I will show in detail only a couple of constructions, in particular from finite geometry. So from now on, let Pg and Q be the projective space of dimension n over Fq. A resolution class of Pg and Q is a set of lines that partition the set of points of the projective space. And the packing of the lines of Pg and Q is a partition of the lines into resolution classes. So these are well-known and classical objects from finite geometry that allow us to obtain k-partial packings as in the previous definition. Indeed, we can take as X the set of points of the projective space, and we can consider any k-1 resolution classes from a certain packing of the lines of Pg and Q. Because in this way, clearly these k-1 resolution classes are k-1 partitions of X, and they also satisfy properties A and B, because here the subsets that we are taking are the lines of the projective space. And so any line has at least 2 points, which means that property A is satisfied, and two distinct lines meet at most in 1 point, which is exactly property B. So at this point, by applying the lemma of Fazeli, Varda, and Jacobi, we have that from a packing of the lines of Pg and Q, we obtain k-partial packings, and so we obtain k-server PIR codes. Sufficient conditions for the existence of a packing of the lines of Pg and Q are well known. For instance, we can assume n and q as in these two cases. And with this assumption, we prove the existence of a family of PIR codes with this dimension, a certain number of servers, and this length. In particular, observe that the storage overhead of this family of PIR codes has this shape, where if we fix k and we let q go to infinity, we can see that this parameter goes to 1. So this family of PIR codes is asymptotically optimal in terms of storage overhead. Other objects from which we can obtain k-partial packings are maximal arcs. Here, Vz maximal arc K is a set of V points of the projective plane with the property that every line of the plane is either disjoint from K or it meets K in exactly Z points. And how can we obtain k-partial packings from these objects? First of all, observe that if we take a point outside the arc, then the set of lines through this point that are not disjoint from K clearly define a partition of K. So if we take several points outside the arc, we obtain several partitions of K. In particular, if we take Q plus 1 collinear points outside the arc, so we have Q plus 1 partitions, by taking k minus 1 of these Q plus 1 partitions, we will obtain a k-partial packing. Here the proof is similar to the one I showed before, because again we are taking lines of the projective space, and the only observation is that we cannot take 2 points lying on a secant line to the arc, because otherwise two distinct partitions will share a subset, so property B will not be satisfied. Also in this case, the existence problem for maximal arcs has been completely solved. And so by using this existence result, we obtain this family of PIR codes with certain parameters. And in particular, again, if we fix k and we let n and n prime go to infinity, the storage overhead of this family of codes goes to 1. Here you can see some of our other constructions. Again, the first three are from finite geometry, in particular from classical unitals, the set of internal points to a conic, and from affine geometry. It is also possible to construct k-partial packings considering a group with this shape, so the direct product of a certain number of cyclic groups, because here each of these cyclic groups naturally defines a partition of G, and these k-1 partitions will satisfy the property of a k-partial packing. And also, apart from the approach with k-partial packings, other remarkable objects from design theory that allow to obtain PIR codes are configurations. Here, a VT-BZ configuration is a set of V points, B lines, such that on each line there are Z points, and through each point there are T lines. And with the additional property that through 2 points there is at most 1 line. It is possible to apply the lem of Fazeli-Vardi and Jacobi to these objects to obtain a certain family of PIR codes. Finally, it is also possible to combine these two approaches, the one with k-partial packings and the one with configurations, to obtain new families of these codes. So to conclude, you can see in this slide a table with the best known PIR codes for small values of S, the dimension, and K, the number of servers. In this table, for each choice of K, you can see 2 columns. In the first one, there is the length of the best known PIR codes in the literature, and in the second column, there is the corresponding storage overhead. The values in red in this table are our improvements over the existing literature using the approach of k-partial packings and configurations. So that's all I wanted to say, and thank you.